Hi everybody, today we're doing an introduction to predicate logic and the role of quantifiers. We're going to start out by looking at the difference between propositional and predicate logic. Propositional logic deals with simple statements that are true or false, like 3 plus 4 is equal to 7. Predicate logic includes variables and quantifiers like for all and there exist, which could look like p of x is x plus 4 is greater than 7. This time notice we have a variable x, which means we're not sure if p of x is true or false. Along with our statement, we always need to include a domain, like the set 8, 9, 10. Then we can test the truth of the statement over the domain. Quantifiers help us talk about these multiple elements that are in the domain. We have two symbols. One of them is called existential, meaning it exists. So maybe we say there exists or at least one. We also have a symbol that's universal that stands for every or for all. For our statement P, where x plus 4 is greater than 7 over the domain of the set 8, 9, 10, we can say for every x, P of x, because 8 plus 4 is greater than 7, 9 plus 4 is greater than 7, and 10 plus 4 is greater than 7. So for every element in our domain, P of x is true. Let's try this example. We're going to let P of x be the predicate x is divisible by 5 with the domain D that's equal to the set 3, 5, 7, 9, 11, 13, 15, and 17. We want to know which elements in D make the predicate P of x true. We need to look through the set D and find all numbers that are divisible by 5, which in this case are only two of them, 5 and 15. Let's change our example. This time we have our domain is 1, 2, 3, 4, 5, 6, 7, 8, 9, and we'll let the predicate P of x be x is greater than 5. Again, we want to know which elements of D make P of x true. So we're searching through our domain and looking for all numbers that are greater than 5. That means we want 6, 7, 8, and 9. We don't use 5 because 5 is not greater than 5. Let's define a second predicate. We'll call it Q of x, and this time x is going to be less than 8. We want to know for which elements in the domain is this predicate true. So back to our set D, we're looking for all numbers less than 8. That means we have 1, 2, 3, 4, 5, 6, and 7. Let's put those two things together and find the elements of D for which P of x and Q of x are true. So we're finding the intersection of P of x and Q of x, which means we just have 6 and 7, which are in both of our previous answers. Let's change P of x to be the predicate 6x plus 3 is odd. Then we're going to evaluate P of 5 and decide if it's true or false. To start out, we'll plug 5 into 6x plus 3. That looks like 6 times 5 plus 3, which is 33. So our question is this odd? Which it is, so we would say true. Let's think about how this helps us with using our quantifiers. What does P of 5 tell us about there exists x P of x? There exists x P of x must be true because P of 5 was true. Let's carry that on to the universal quantifier for every x P of x. This could be true or it might not be true. We don't know the whole domain, so we can't say if P of x is true for every value of x, but we do know it's true for at least one value of x. Q of x be the predicate x squared minus 1 is prime. We're going to test Q of 4 and find out if it's true or false. That means we're going to square 4 and subtract 1, which gives us 15. So our question is that prime? And the answer is it's not. That's false. This time when we look at Q of 4 and what it tells us about there exists x Q of x, we have to say it could be true or it could be false. We can't tell based on one singular value. But we do know something about the statement for every x Q of x. This has to be false. Since we found one value that's false, we know every value cannot be true. In our next example, we're going to use the same domain D, which is the set of numbers -4, -2, 0, 2, and 4, to test the quantifiers. The first one says for every x in D, x is less than 5. This is true. All of our numbers, -4, -2, 0, 2, and 4, are less than 5, we say true. Next, we have there exists x in D where x squared is greater than 10. So I just need at least one number that when I square it, it's greater than 10. It turns out I have two numbers, 4 squared is 16, negative 4 squared is 16. Those are both greater than 10, so we can say true. Next, we have there exist x in D, where x plus 3 is equal to 9. Here's our first problem. The highest number I can have, 4 plus 3, is only 7. I don't have a number that when I add 3, I get the value of 9, so we'll say this is false. Next, we have for every x in D, x is greater than negative 4. We are close on this one, but it's not actually true. Negative 4 is not greater than negative 4, so it's not for all x, it's for most x. Because it's not for all x, we say false. Our last one says there exists an x in D where x is greater than negative 4. This time we have an existential quantifier versus a universal quantifier. With an existential quantifier, I only need one true. I have multiple times that my value in D is greater than negative 4. I could use negative 2, 0, 2, or 4. So for the existential statement, I can say that is true. Let's look at this as a quick summary. When I have for every x, p of x is true, that requires that every element in the domain makes p of x true. When I have there exists x, p of x is true, that means I have at least one element in the domain that makes p of x true. So we have every versus 1. The flip side of that is for every x, p of x is false. This requires that one element in the domain makes p of x false. I don't have to show all of the elements are false, I just have to show that the statement for every x, p of x is not true. If I have there exist x, p of x, and that statement is false, that does mean that all of the elements in the domain make p of x false. I can't have any times that this statement is true if there exists is going to be false.